Good evening, ladies and gentlemen. Welcome to the third day of our Nobel Week dialogue. Today is for physics. Yesterday we had chemistry. And on Monday we had medicine/physiology. My name is Bola Ogunṣeye. I'll be your anchor for the night's event. Please permit me to bring on board Professor Olufemi Bamiro, a committee executive member an executive committee member of IACD, a professor of Met Engineering, and a former VC of University of Ibadan. Professor, you're welcome, sir.
Thank you very much. Thank you. So, or do I go ahead?
Please.
Okay, go ahead.
Please go ahead.
Okay, thank you very much. Well, first and foremost, let me express my sincere appreciation, to the organizers led by Dr. Kolade Mosuro for this invitation. I must say that when I got the invitation, I was more or less curious that Nobel Week, what will it be about? Nobel, one would be thinking that this is a high-level scientific or what have you. So I was curious. Well, of course, thanks that he told me that I'll be participating in the third day, which is devoted to physics, whether that will be chemistry, then medicine before then. So because of that curiosity, I chose to attend both Monday and Tuesday. I was here. I participated in the Monday event as well as Tuesday, just to see what it was all about. I must say that I cannot but praise the organizers. What you have sought to achieve through this, program. It's really fantastic. I'm sure, yes, this is the first time it's been done, but I'm sure subsequently when people get to know about this, a lot more people will be, attending. I cannot but also praise the panelists. The panelists, the Monday, Tuesday, for the excellent work that they have done. Simplifying, one cannot but appreciate that it's a challenge for somebody to simplify what is not simple. And of course, Dr. Kolade Mosuro did say that, you operate on the notion that nothing can be so abstruse that a disciple that cannot but, be able to understand and explain it to the layman. That quickly reminded me of our inaugural lectures in the university system. We always say that inaugural is gown to town, and that no matter the complexity of what somebody has done by way of research, by the time you are giving your inaugural lecture, you just have to realize that you are not talking to your colleagues in that field, you are talking to the generality of people. You must be able to simplify. It also reminds me of what a statement by Einstein, to the fact that if you cannot explain it to a layman, it means you are still to fully understand the phenomenon. I must say the panelists, have really shown a great understanding. Now, in respect of the works and endeavors leading to the award, from what I could gain from the past 2 days, we've been able to see multidisciplinarity among those who, people coming together from different disciplines and working, and even interdisciplinarity, meaning that the emergence of new areas, of research. But most importantly, we have also witnessed collaboration across national, borders and so on. We've seen different nationalities, coming to, to really work together, to really make, to achieve what we have seen, leading to the award of the Nobel Prize. Now, I now ask myself, in respect of, statistics, or looking at literacy in physics, I said, well, what has happened in physics? Then, of course, I reminded myself of the statement we say that that the world economy will never now pay you we never reward you now for knowledge. We keep saying knowledge, knowledge, knowledge. Knowledge is no longer enough.
Professor Bamiro, there's a freeze from your end. Professor Bamiro has just left the table, but he's going to sign in again. He must have a little glitch in his connection. Please bear with us. He'll soon be back with us. Again, I repeat, Professor Femi Bamiro, the chair for this evening's event, was on giving his speech when we had some technical problems. But I reckon he will soon be with us. Now he's joining in again now. He's joined again, and I'll set him up again. Well, Professor Bamiro,
yeah,
we lost you temporarily for about a minute or so. But,
yeah, I will quickly conclude now. Okay, can I quickly conclude? So
please go ahead, sir.
So what I've called, looking into the awards in physics, what I've been able to find out is that over time, that there have been 215 awards that have been made since 1901, when the first award was made to a German, and that so far, only one person has won it twice, in 1956 and 1962. Then Wilhelm Bragg won it in 1950 at the age of 25. Then for women, 4 women have won the prize. Then Albert Einstein won it in 1921, although the award was given in 1922 on his work on photoelectric effects. And then an Indian national won it in 1930 based on his works. And you could see when you Google, the different nationalities, people working together in corporate, and the different areas in which they have worked. And I saw the different areas that even people like us, when we were doing physics, Nekon and Parker, way back, these were people who really have gone beyond, that level. Series of works, electron microscope, X-rays, and things like that. So, and of course, moving to the present day, a lot of them leading to equipment, X-ray machines, low temperature physics, and things like that. A lot of work has been done, leading to various equipment. And even now, we are moving to biomedical engineering, involving a lot of diagnostic equipment being developed. So a lot of work has been done, that we can see. And finally, I just asked myself, okay, coming home, how far have we, how well have we done in physics? The area of physics. And I said, wow, if we go back to the 70s, 80s, where in our physics department in UI, we had the like of Professor Webb, Professor Ete, Madumezia, Giwa, Babalola, and of course, outside of there, in the mathematics, SLO, and all these other people. I had the opportunity of being, when we come to, people working together, we had the opportunity of a research establishment in Italy, Trieste, where we were able to, I was able to interact with these giants. And it's quite, I don't know whether it's still going on now, but there's no doubt, as we have seen and come to that, you need a lot of collaboration and exposure, to be able to do, this type of high-end, research. And I'm happy that somebody like Professor Farai is here, to be able to play the role of of really taking us through the current three. I saw three when I Googled it. I saw that 3 Nobel laureates in 2020 in physics. But all the same, I think we have a lot to learn, and I'm sure this program must continue. And I look forward to even researchers gaining a lot, from this, program to see what others are doing and what we should do to be able to advance, knowledge. Beyond the ordinary. So thank you very much. Okay.
In physics, with one half to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. And the other half jointly to Andrea Ghez and Reinhard Genzel for the discovery of the supermassive compact object at the center of our galaxy. And you have the pictures of the new Nobel laureates on the screen behind me. Roger Penrose was born in Colwich in England and got his PhD at Cambridge University. He's now emeritus professor in mathematics at the University of Oxford. Reinhard Genzel was born in Bad Homburg vor der Höhe in Germany. He got his PhD at the Universität Bonn and is currently director at the Max Planck Institute for Extraterrestrial Physics in Garching in Bayern in Germany. And he's also a professor at the University of California at Berkeley in the United States. Andrea Ghez finally was born in New York City. She got her PhD at Caltech in Pasadena in California, and she's currently professor at the University of California, Los Angeles in the United States. Thank you, Jeroen. On behalf of the Nobel Committee for Physics, I would like to congratulate the laureates in receiving the 2020 Nobel Prize. This year's prize celebrates the discovery of one of the most exotic objects in our universe, the black hole. For many years, physicists questioned the very idea of a black hole, treating it as a peculiarity in our theory of gravity. Roger Penrose showed that black holes might really exist, forming in a stable and robust process consistent with the theory of general relativity. Reinhard Genzel and Andrea Ghez led research teams to make precise observations over many years, which pointed to the existence of a supermassive black hole in the center of our very own galaxy. My colleague in the Nobel Committee for Physics, Professor Ulf Danielsson, will tell us more about the contributions of this year's laureates to the discovery of black holes. Good, David. And now the floor is yours.
As early as the end of the 18th century, the English astronomer John Mitchell and the French scientist Pierre-Simon Laplace speculated that there might exist objects with a gravity so strong that not even light can escape. We now call such objects black holes. To create them, you would need to compress the sun into a region only a few kilometers across, or to squeeze the Earth down to the size of a pea. But it was only in 1915 when Einstein formulated his general theory of relativity, that we had a mathematical framework powerful enough to describe such objects. Physicists, Einstein himself included, were confused for decades. The mathematics was too complicated. Could something like that actually occur in a real universe? And then, in 1965, inspired by the discovery of new violent phenomena in the universe in need of an explanation, Roger Penrose published a remarkable paper. He introduced new mathematical tools and proved with mathematical rigor that the formation of black holes is an inevitable consequence of general relativity. In a universe governed by general relativity, the formation of black holes is a natural and expected process. Let us study now a black hole a little bit more closely. In general relativity, there's an intimate relation between gravity and time. Down at my feet, time runs a trillionth of a second slower per hour than it does up in my head. And if you have a black hole, time even seems to stand still at the horizon of the black hole. Now, I can point towards the black hole and say, there it is. There is the center of the black hole. My finger is stretched along a direction of space. But if I then bring my finger a little bit closer and let the tip of my finger go through the horizon and enter into the interior of the black hole, I will make a startling and somewhat worrying discovery. The direction inwards is now time, and the tip of my finger will be in my far future, and it will be as difficult to pull my finger back out again as it would be to travel backwards in time. Furthermore, my finger will be torn apart, and the tip of my finger will be carried by time all the way into the center of the black hole, where time itself ends, and the known laws of physics cease to apply. But if such objects now actually exist in the real universe, then how could you find them? Well, actually, already in 1783, John Mitchell had an idea. What if there are other luminous objects, such as stars, moving around the black hole? Then one could infer the existence of the black hole by following the motions of the stars. But it would take more than 200 years before this dream would come true. And it was Reinhard Genzel, Andrea Ghez, and their teams who did it. They turned the telescopes towards the center of our galaxy, 26,000 light years away, where there were suspicions that something strange was going on. The heart of our galaxy, the heart of the Milky Way, is hidden inside of a dense cloud of dust. And you have to look in the infrared to reveal its secrets. What they found was incredible. They could see several stars moving around something that they couldn't see. And it was one star in particular that caught their attention. It took the star around 16 years to complete its orbit. At closest approach, it was no more than 17 light hours away from the invisible object. Calculations show that 4 million solar masses is hiding there. There is no other explanation than a supermassive black hole. This year's laureates have uncovered secrets in the darkest corner of our universe. But this is not just an old adventure coming to its triumphant conclusion. It's a new one beginning. As we probe ever closer to the horizons of the black holes, nature might have new surprises in store.
Good evening once again, ladies and gentlemen. It is my pleasure and honor to bring in our panelist for today, Professor Idowu Farai, a professor of radiation and earth physics, as well as our moderator for tonight, Dr. Oluwashina Adegoke. You're welcome, gentlemen. Prof, your answer.
Mute. I want to talk now. Share screen. Good evening, ladies and gentlemen. It's my pleasure to participate in this Nobel Week dialogue. I must say that it's one of the most exciting things I've experienced in this new year, this year 2020. I mean, after all the lockdowns and all the rest, so it's good to have some excitement in this fall. I'd like to thank the organizers of the week for counting me worthy to be a partaker in this dialogue. The topic is Nobel Prize in Physics 2020, Relevance to Mankind. My name is Idowu Farai. I'm a professor of physics in the University of Ibadan. So you are welcome on board, everybody. Our Nobel Prize in Physics 2020, 3 laureates shared this year's Nobel Prize in Physics for their discoveries about one of the most exotic phenomena in the universe. Nobel Prize in Physics 2019 happened to be in this same area of astronomy. It was for contribution to understanding of the evolution of the universe and the Earth's place in the cosmos. So the 3 laureates, as we have just had, Roger Penrose, Rehan Gezel, and Andre Ghez. We have been, they have been introduced to us in the previous discussion. Now, the first question we'd like to ask is, what is astronomy? Astronomy is the study of the physical universe and its contents. There are 3 main branches to astronomy. We have 1, astrometry, which is positional measurement of the stars and the planets in the celestial sphere. We have the celestial mechanics, relative motions of a system of bodies, and the associated gravitational fields. Then we have astrophysics, which is talking about the internal structure of the planet, the stars, and the moon, and their consequence on external forces and position of in the celestial sphere. Usually, what we know and what we hold on to are based on the convergence of these results. Various branches should get the same result if the result is valid. So anyone that is not yet proven by another branch is always classified as inconclusive. So that's astronomy. Then the universe is so vast and limitless, and it has been the curiosity of mankind since ancient times. We are always interested in the matter within the universe. That's talking of the planets, the moons, the stars, galaxies, and what is in between them. Then we are always interested in the energy that is present, that is holding these bodies together. We are always interested in dimensions of space, time, and their contents. Then scale of measurements. Usually, this is far beyond the ordinary, and often it is difficult to comprehend. I mean, it's difficult for somebody to comprehend time in billions and billions of years. When an individual will live maximum 100 years, then you are imagining what is happening in trillions of years. It's a bit difficult for us to comprehend. Then distance is always measured in light years. That is the distance that light ray will cover in 1 year. It's about 9 trillion kilometers. So this is again difficult for us to comprehend. Then mass of objects in the universe, they are measured in multiples of solar mass. That's the mass of our sun, which happens to be 10 raised to power 30 kilograms. So this again is, where this is more than what we can comprehend. So, but all over the world, there are active research activities going on where they do not have the instruments. There are data they can collect from where they have the monitoring stations, and enough analysis will be made. So we start with the planets. We live on planet Earth here. A planet is a celestial body moving in orbit around a star. The star is fixed, but that is only relative to the planet that we are interested in. We live on planet Earth, which revolves around the sun in our solar system. The Earth, apart from the revolving around the sun, it rotates or it spins about its orbit in 24 hours, which gives us day and night. It revolves around the sun in 365 days, which you call the period, and this gives us the different seasons of the year. Then it has its own satellite, that is the moon, revolving round it with a period of about 27 days. So we have the diagram of the Earth there and its own satellite as the moon. Okay? Now, stars. These are self-illuminating objects that produce energy that sustains various systems in the universe. The star is where energy is produced, and without energy, nothing can happen. So the source of energy in the universe is the star. We are on Earth here because the sun is there to give us energy. The spectrum of radiation from a star is quite wide. It ranges between X-rays and the radio waves, so wide, and is a source of information. It gives information about the stars, about its temperature, the composition, age, mass, intrinsic luminosity, and everything about a star. can also always be inferred from its spectrum. And it is highly unlikely that two stars will have exactly the same spectrum. So we classify them according to their spectral characteristics. The stars are the most widely documented astronomical objects, and hence our main source of knowledge about the universe. Many stars are known to have planets, which we call exoplanets, revolving around them. So it's not only our solar system that we have planets revolving. There are other stars having planets revolving around them, and they are called exoplanets. Now, talking about our own solar system, the position of the sun. The sun is at the center of our own solar system, is our own star. The position of the sun is fixed relative to the 8 planets revolving around it, with gravity providing the centripetal force. The closest planet, that's Mercury, completes one revolution in 88 days, while the farthest, that's Neptune, completes one revolution in 165 years. The third planet, that's our own Earth, completes a revolution in 1 year, which is 365 days. The masses of stars and other objects in the universe are expressed in the unit of solar mass. So that's the solar system there, with the 8 planets, with the closest being Mercury and the farthest being Neptune. Okay. Then, how does a star originate? That we call it, we are interested in stellar evolution. That's stages of life for a star. Most of the universe is vacuum, except some places where you have some thick, relatively thick density of matter, consisting 75% hydrogen and 25% helium, and a few heavier elements. Regularly within the universe, turbulence deep within these clouds can make them to start lumping up, and they start to grow. And once they now form a particulate matter and they come together, gravity sets in and bring more particles on, and the cloud now start to condense and get bigger, more compressed. Fragments in the process can fall out to become planets, astronauts, comets, and other dust. As the knots collapse further, the material at the center begins to heat up and get hotter, and at that point we call it a protostar. That's a baby star, more or less. Can we take this in? Sorry about that. Just I have so many things disturbing my. Okay. So the protostar gains mass. Its core gets hotter and more dense. At some point, the core is hot enough at about 15 million Kelvin. At that point, the nuclear fusion of a helium, of a hydrogen to become helium starts. That 4 hydrogen atoms will fuse together to become a helium nucleus, and a lot of energy is released. In the process, radiation, that's energy in form of heat, from this reaction keep the star from getting closer and becoming collapsed and going into extinction as a result of collapse. During this is the stage we call the adult life of the star. That's the diagram I'm trying to show there. There is a nuclear fusion within the star. There is gravitational force compressing it. There is a balance, an equilibrium between those two forces. A star like our own sun requires about 15 million years to get to maturity from the beginning of the cloud coming together. So now that's for the star. What do we call a galaxy? A galaxy is a family of stars, an organization of stars and dust as a separate but not necessarily independent system. The galaxies have a way of interacting with one another. They may be sharing a common motion. Our own galaxy, that's the galaxy to which we belong, is called the Milky Way. It contains over 200 billion stars and enough dust, enough matter and gas to make billions more. So the solar system, that's our own solar system, is about 30,000 light years from the center of the Milky Way and about 20 light of the plane of the galaxy. And there are about 300 billion galaxies in the observable universe. So it's almost like there is no end. Now, when a star gets to maturity, what happens to it eventually? From birth to maturity and to eventual death, a star lives for billions of years, depending on its size. The longest phase is the adulthood phase, when the star is said to be in the main sequence. The bigger the size, the shorter the main sequence. A medium star, like our own sun, will spend about 10 billion years on the main sequence. The eventual end of the star starts when the core runs out of hydrogen. Once it runs out of hydrogen, there is no energy from within to balance the gravitational compression. So the star now is going to start another phase of its life and eventual death. Insight from the theories of general relativity and quantum mechanics show that the eventual fate of the star depends on its mass. How one goes out of existence is different from the other, depending on the mass. Now, end stage of stellar star evolution. A medium star with a mass less than 8 solar masses will end up as a small hot ball called white dwarf. That is an object which gravitational force and force due to pressure of electron gas will balance, but it will be so small that we call it a white dwarf. That's a star with less than 8 solar masses. That's what will happen to our own star. That's the sun eventually. A more massive star, the ones that have masses greater than 8 mass of the sun, we end up as a neutron star, where the pressure from outside cannot balance. It's more than the pressure that the electron gas can produce. So the pressure from outside will force the electrons into the nucleus, such that protons and electrons will combine will neutralize to form neutrons. So the pressure from the neutrons will keep this collapsed object, the mass, and such end is called the such a star at that stage is called the neutron star. If, however, the neutron star is massive, it's more than 3 mass of the sun, the neutron pressure cannot balance the gravity from outside, and the star will collapse completely into a black hole. Now we are getting to where we are going. All stars with initial masses greater than 20 mass of the sun are expected to end up as black holes. The smaller ones can end up as white dwarf neutron star. Okay, this is what I'm saying. This is the life of a star. It starts with the clouds coming together. At that point, we call it the nebula. If the mass is small, it enters the main sequence. So our own star is in the main sequence presently and is giving us light. So in about, when it spends about 10 billion years in that main sequence, it becomes what we call red giant, and later it becomes a planetary nebula, then eventually becomes a white dwarf. That's for those stars that have their masses less than 8 times the mass of the Earth. For those that have their masses higher than that, of course, they are big stars. They are in their main sequence, they illuminate brightly. If you look up in the sky, when the scene is very good, you will see some stars that are very bright, brighter than others. Those ones are the giant stars in their main sequence. When they die, they become super giant first, then supernova. Then some of them will become neutron stars. Then some, the very big ones, will become a black hole. So black hole is the ultimate end for a big star. That's the point I'm trying to make. Now, let us look at the black hole, the phenomenon. Now, from Newton's gravitational law, we know that there is a force on any object M, any mass M, that is in the gravitational field of another object of density rho and radius r. That force simply is given by that expression. You can assume every other thing is constant there except the density. So the force that attracts objects to other objects depends on the density of the object that is creating the force. So a black hole is an object with so much high density that its gravitational field prevents anything, including photons of light, from escaping. And if light does not come from an object, that object will look black. So that's how the word black. And in the area where it is, once you cannot see it, it will look, and it's black, you will now picture it as a hole. So that's the origin of the word black hole. It's not that it's a hole, but it's a ball or a mass that is so dense that light cannot escape from it. And if light does not escape from it, you can't see it, that region will be black in the and the surrounding will be brighter. So you picture it as a black hole. You can see the picture there. The surrounding is brighter. Black holes are surrounded by a disk of material called accretion disk with differential rotational motion around the black hole. Most black holes are detected through the emission of X-rays and optical rays coming from their accretion disk. Some don't have any accretion disk and they are not seen. We just, I mean, maybe when we are simulating, we get that they are there. That's their end, of course. So it's not every black hole that is visible. It's only when it has a bright accretion disk around it. So there are two types of black holes. One, we call it stellar mass black holes. Those ones are the commonest. They are almost everywhere. That's when every big star dies, it becomes a black hole. So all of them, there are 200, 300 billions of them in space. And their masses are between 3 to 100 mass of the sun. There is the other group with masses in the range of millions of mass of the sun. That's another group. There are fewer. And we are going to talk more on them this evening. There are inconclusive evidences that there is an intermediate mass black holes in the range between the stellar mass black holes and the supermassive black holes. There are about 1 billion stellar mass black holes in our own galaxy alone. Of course, other galaxies have their own stellar mass black holes. There are evidences that almost every large galaxy has a supermassive black hole at its center. The biggest black hole, supermassive black hole, is about 21 billion times the mass of the sun. These are things that have been suspected. I told us there are different branches of research. So maybe one or two incidences have indicated that such bodies exist, but we cannot say they exist unless they are proven, as we will see for the lecture of today. So this year's Nobel Prize in Physics, I call it a year of black holes. This year's Nobel Prize in Physics focuses on black holes, which are amongst the most puzzling objects in the universe. Two breakthroughs were recognized, and the man who did the introduction told us this at the beginning. One, establishing that black holes can form within the theory of general relativity. That is, general relativity had predicted correctly that such bodies will exist. That's the one that one of the Nobel, one half of the Nobel Prize went for that discovery. Then the second half went to the discovery that there is a supermassive compact object within our galaxy. And this is at the center of our galaxy. So this went to the two recipients that were introduced earlier on. So we want to see now, what did they do actually? And how has that, how is that relevant to mankind? Now we understand these things if we look at Einstein's relativity. And I'll do my best to bring this to our level, as Professor Bamiro had already said, that how much you can explain it will show how much you think you know it. And I think I know it. I hope I can explain it to all of us. One, the theory was proposed. There are two sides to the Einstein's relativity. There is the one special theory of relativity, 1905. This one is about the law, which says that the summary is that laws of physics are the same in all non-accelerating observers. Then speed of light in vacuum is independent of the motion of who is observing it. That's another fallout from a special theory of relativity. Then space and time are interwoven into a single continuum that we now call space-time. So there are now another dimension to the three dimensions we always know. We know about X, Y, Z axis to locate a point in place. But there is the element of time too, because so if anything happens to time, it may affect position. Then a big fallout from the special theory of relativity is this legendary equation of Einstein, which says energy and mass are equivalent. That is, if you have mass, you have energy. Or if you have energy, you have mass. That's E equals mc squared. And of course, this is the basis of the atomic bomb. So that's why people will always say that Einstein introduced the atomic bomb. That may not be correct because Einstein postulated his theories way back 1905. Atomic bombs were invented in 1940s. So it's just consequence of the Einstein's theory. That's the first theory. We call it special theory of relativity. The second one, which was proposed by Einstein 10 years later, that's in 1915, now says that massive objects in space-time will curve around them, resulting in curved paths that all objects around them will follow. Gravity, as a matter of fact, between objects arises from the distortion in the fabrics of space-time. If you look at that object, it's like that thing should be horizontal. In the ordinary, when we are not dealing with a relativistic physics, that net should be horizontal. But when we are dealing with massive objects and you put it on that carpet, the thing will distort. And by how much it distorts depends on the mass that is resting on that net. The net is the space-time plane, the graphic of space and time. The distortion, that's that hole there, is called the gravity well. So the bigger the mass, the more the distortion, and the deeper the gravity well. So the next question is there a limit to how much mass can stay on that net? Will there come a time when the net will sink and all the thing will be trapped there? So that is as far as Einstein is concerned. So between 1915 and 1965, various scientists were trying to project further that what happens when that mass is big enough. It was in 1965 that, so the implication of that net is that there is the possibility that if an object is massive enough, it could rip a hole in that net. It could rip a hole in that net, and there's that sheet of space-time. And if it rips a hole there, it forms what is called a black hole, because that thing will go down to a point of no return. So black hole solutions to Einstein's equation were regarded as purely theoretical speculation, describing an ideal situation in which stars and their black holes are perfectly round and symmetrical. Nobody took anybody serious. So up till 1965, it was in 1965 that Roger Penrose brought out a paper which he called Gravity Collapse and Space-Time Singularities, that a star of sufficient mass will always collapse into a black hole. It was an ingenious mathematics. I hope nobody will ask me to restate that math today, because it's not an easy one. So that is what Penrose did. And Penrose's work now shows that at the boundary of a black hole, which is called the event horizon, one will have to go faster than the speed of light to escape. That is the event horizon. That you see that net has now, a hole has been punched in it, and the down there, you see it's moving only in one direction. It cannot come out. As that man was trying to show us the other time, that if you stick an object into that hole, it can only go down, it cannot reverse in time. We cannot have what happened yesterday, go back in time. So this goes to a point of singularity. And the whole of that region, that red, blue, this is called the event horizon. And if an object goes there, to come out, we need an escape velocity greater than the velocity of light. And that is not possible. Velocity of light is the limit of velocity. So to go into that place, there will be no escape. So if light cannot come out, then the thing appears black. So it's now that every other thing that we observe is pointing towards what this Penrose man had proved, that we now recognize 55 years after that the man was right, and he was awarded half the 2020 Nobel Prize in Physics for the discovery that black hole formation is a robust prediction of the general theory of relativity. It predicts that body. So before that, we didn't know how to explain black holes. Now, that's about Penrose and his work. Then the other two astronomers, one in Germany, the other in the US, they have for many years astronomers have for many years been receiving strong radio signals from the center of our galaxy. And these radio signals were being analyzed, and there is the suspicion that there must be a black hole there, or there must be some objects there. And of course, if stars that were seen to orbit around that place, they could only be orbiting around the gravity of some objects. So for many years, there were speculations that there is an object at the center of our galaxy about which the stars were rotating. This center was given the name Sagittarius A star. Towards the end of 1960s, it became clear that Sagittarius A star occupies the center of our Milky Way, around which the stars orbit. There is particularly a cluster of stars orbiting around Sagittarius A star with periods short enough for us to measure. See, when we talk of time in the astronomical world, we talk of billions of years. But in around the Sagittarius, some stars were moving, and their period, that is the time they take in completing their orbit, is in just a few number of years. So it was then easy for them, these astronomers, to pick some 30 stars to study. So let us now look at André Ghez and Reinhard Gess's contribution. André Ghez and Reinhard Gess in separate, in separate research group that proved the center of gravity of our, the center of our galaxy, the Milky Way, since early 1990s. Both groups tracked about 30 of the brightest stars within this region. I told you their period, their time to complete a round trip is short enough for us to follow. One of the stars, which they call S2 or SO2, completes an orbit about the center of the galaxy in less than 16 years. 16 years is just a blink of an eye in astronomy. So S2 is a young star, so it's quite bright, and it's about 15 times more massive than our star. So it's brighter, so it can be followed. So we have been told the resume of Andre Ghez and Richard Gesell in the introduction. So the one is in UCLA and the other is in UC Berkeley. They work together. I mean, they work separately, but their results were always in synchronization. They are getting the same result, which confirms that what they are getting is correct. So they mapped the orbit of S2 around the Sagittarius A star. So the region contains a significant number of dust, so that the best way to probe this star was by radio or infrared rays. If you use optical rays, the thing will be absorbed by the dust. So it's only infrared and radio waves that could penetrate through the cloud, the dust around this this star. So in that region, Andre Ghez and her team at UCLA use a 10-meter telescope based in Hawaii. Richard Gesell and his team used another telescope, we call it VLT telescope, in Chile. Both groups took advantage of the high precision and sensitivity of this large telescope. The larger the telescope, the further it can probe the space. So these were the biggest telescopes that we have today. Look at the very large telescope in Chile. It's in an array of 4 telescopes mounted. And that particular site is because of the atmosphere around that place, very clear, unlike in the tropics, where there will be so much particles that will absorb the rays when they are coming to the, so they need special sites. So they could get one on Paranal Mountain in Chile. That's where Richard Gesell and his group worked. Then Andre Ghez and her group, they have a twin telescope at Kess Observatory in the mountain of Mauna in Hawaii. The two of them were following the same star. They were following the same star so that they could, from time to time, compare their notes. So both groups started mapping the site since 1992. The period of motion is less than 16 years. So in 16 years, an orbit will be completed. Then the first orbit was, the first round trip was completed in 2007. And currently, the star is on a second cycle since they started monitoring. But from the first cycle and the journey so far, a lot have been revealed about the orbit of that star. The smallest diameter of the orbit, you can see the shape is elliptical. So the smallest diameter at that center there is about 400 AU. AU is astronomical unit, and it's 1 AU is distance of the Earth to the sun, which is about 150 kilometers. So about 400 times the distance of here to the sun is the width or the diameter at the smallest point there. S2 was closest to the center, that is the Sagittarius, at a distance of 120 AU in 2002 and 2018. you can, that's the position, that star there is the position of the Sagittarius, and the orbit, you can see the distance is so close, just about 120 the distance from here to the sun, 120 times. So it's close. And why is that important? At this closest point, the gravity of Sagittarius is so fierce that it has to accelerate to about 7,000 kilometers per second relative to Sagittarius. 7,000 kilometers per second. That means you move from here to New York in less than a second. That is the speed with which it moves at that point. And at other distant points, it was moving much slower. At this close range, relativistic effects such as gravitational redshift in wavelength of light from that star, as predicted by Einstein's general relativity, was observable. There was a shift. If you are monitoring it at a particular wavelength in the red zone, at that point, the thing shifted to another wavelength. That had been predicted by Einstein. Also, the star's orbit does not remain stationary, but it moves forward. On the second trip, it moves forward, creating a phenomenon that we call Schwarzschild precession, close to the galactic center, again as predicted by Einstein. So it appears that Einstein's relativity is applicable or is more relevant to astronomical dynamics more than what we see here on the Earth's surface. So what happens? By applying Kepler's law of motion, the position, the velocity, and every other detail that is needed was used to estimate the mass of that object. The mass of the central object about which the star was orbiting was calculated using Kepler's laws of motion. That's simple laws of motion. You do that in your A-level physics, the Kepler's laws. You put in the mass. The resulting mass that was enclosed as Sagittarius A star was found to be 4.6 mass of the 4.6 times 10 raised to power 6. That's 4 million times, more than 4 million times the mass of the sun. Million times more than this thing. Whereas its size revealed that it occupies a small what's that? Something is covering it. A small what's wrong with you?
Small region.
A small region of about 44 million kilometers. There is something covering it here. 44 million kilometers. 44 million kilometers. That's the diameter. Meanwhile, the mass is 4.6 million times the mass of the sun. If you know the mass of the sun, that's 10 raised to power 30. Multiply that by million. That's you're talking of 10 raised to power 36 kg. For an object that has a small size of just 44 million kilometers. This large mass compared with the small mass of the Sagittarius suggests that it must be the stars must be orbiting a supermassive black hole. So because of this discussion, this discovery, the two of them were awarded half the Nobel Prize in Physics for 2020 jointly for the discovery of a supermassive compact mass at the center of our galaxy. Now you ask, what's the implication? It shows that every other galaxies, the 300 billion other galaxies in the universe, will invariably have their own super massive black hole in there. So it's a major discovery. So nobody is now left in the dark as to what happens to the stars as they move around the galaxies. So it's a major breakthrough in knowledge, and we think they have really earned their prizes. Thank you very much. That's my little presentation. So I don't know if there are questions that we can answer to throw light, but more light to what I have discussed. I probably haven't touched on everything. Thank you. No.
Hello?
Okay, yes.
Hello?
Yes. Okay. Yeah, we can hear you.
Hello?
Hello.
Hello?
Hello. Hello.
Dr. Adegoke, there's a background noise coming from your end. Please, if you control that, you'll be able to gather the questions and be able to feed the questions to Dr. Adegoke, the floor is yours.
Okay.
Okay.
It's been a great lecture as we are all going to attest to, and many thanks to Professor Father for the wonderful lecture, and thanks to the organizers as well for the privilege to be a part of the program. So, like I have been introduced earlier, I am Oluwashino Adegoke. So we have a couple of questions here that we will attempt to respond to. So I will answer a couple of the questions, and then Professor Farai would also answer others. So without any further ado,
Dr. Adegoke, I'm sorry if I may ask. I think
the
there's
first
another
question
device.
we have is actually from I suppose we all have access to. It's okay, so I guess I'll continue. So the first question, like I said, is from Tayo Farai, PhD civil engineering. So we would like to ask, we would like to have insights as to what happens to time upon encountering a black hole. So a very interesting question. I guess it's a question I'll just try to add. So basically, there are two things we'll look at here. So one is from the point of view of the distant observer, and then from the point of view of whoever is actually going into the black hole. So from the point of view of the observer, the distant observer who is seeing somebody else go to a black hole, So there's a concept of gravitational time dilation that is predicted by Einstein's general relativity theory. And what it says is, as you get closer to a very massive object, time tends to slow down for that person who is going very close to that very massive object. So as you get very close to a black hole, as seen by a distant observer, time is going to slow down for the person who is going close to a black hole, such that when you get to the event horizon, the time is going to stop from the perspective of the person who is a distant observer. So you are not going to see somebody as he goes into a black hole, but as it gets very close to the point where we call the event horizon, time is going to stop for that. And then gravitational redshifting will now come in. So gravitational redshifting basically says, as something moves away from you, the light you get from it gets dimmer and dimmer. So basically, the person who is going close to a black hole, from the perspective of somebody who is very far away, the light coming from that person will get dimmer and dimmer until suddenly you don't see the person again. Now, from the perspective of the person who is actually going into a black hole himself, if we assume where is indestructible, for that person, the time, as far as it's concerned, time will be going on normally as it goes into the black hole. So, Prof will say something more on that.
Let me interject here, Dr. Adegoke. There may be another Zoom user close to you there, because there's a lot of echo coming from your end. But in any event, I think the question now goes to Professor Farai. Just channel the question to him.
Yeah. Thank you. Can you hear me now? Yeah. The question is, what happens to time? The question is, what happens to time when it goes to the black hole? That time ceases to exist anymore. The time stops. Is the ultimate. Time stops inside the event horizon. Time stops. As you go into it, time gets slower. But in the point of singularity, the time stops. There is no time, and you can't go back in time again. So that is the short answer to that question. That what happens to time when it goes into the
thing is, they're
I'm listening. Hello?
Please go ahead, Professor Farai.
Yes, I have attempted to answer that question as briefly as I can so that other people can answer more. Incidentally, the question came from my son. So when that time goes into the black hole, it ceases to, that's the end of time. It's so slow that it doesn't exist anymore. That's it's a bit difficult for us to conceptualize, but that's the ultimate. But nothing goes into the black hole anymore anyway. So, but if it goes there, it doesn't come out. Time is dead there. Thank you.
So we have a second question from Damilari. We have a second question from Damilari, an electrical and electronic engineer. So basically the question is this, an interesting question as well. So hypothetically speaking, what would happen to the planet's orbit if the sun becomes a black hole? That's the question.
Is it what happens to the solar system when the sun becomes a black hole? The sun cannot become a black hole because the mass is not big enough, but it will become what we call the white dwarf, as I showed on. But at that point, the whole system will have disintegrated. And I mean, because the white dwarf cannot sustain the movement around the sun anymore, the mass has decreased, so it's going to cease. that's the ultimate end of our own solar system when it becomes white dwarf. It's not going to become a black hole because the mass is not big enough. I told you black holes start with masses that are bigger than 20 times the mass of the Earth. So our own Earth is just one mass of the sun. So it's too small to become a black hole, but it will change to a white dwarf. And at that point, it cannot sustain the system anymore, and that will be the end. But don't worry, that is in some 6 billion years from now. So we don't know what could have, what will come on, subsequently. But for now, that is what we know will become the ultimate end of our own star. Thank you.
So the next question we have is so there are two questions from this person. So one is what is celestial sphere? Is celestial sphere? So that's the first question. And the second question is has a supernova ever been observed? So I guess
the celestial sphere is the entire cosmos, the entire space. That is the celestial sphere, where we have all these celestial bodies. So the whole sphere is, to say, but that's the universe itself. We call celestial sphere. Then supernova and all the rest, yes, some have been observed, but not conclusively. Not conclusively. The theories project that's what we have. But when you look at, put your telescope in the sky, you see some of them, but some of them at what they emit is not sufficient, it's not strong enough to be picked by telescope. So most of these supernovas and after the life of the star, on the main horizon, it is usually invisible up to the end of their life. That's the much that I can say on that. Thank you.
So there's another question here. I guess the names are not, the names of those asking the questions are not mentioned. So a question is, how can a singularity occur in Einstein's equation if they are non-linear? I guess that's a very theoretical question.
What's the question again?
How can a singularity occur in Einstein's equation if they are non-linear?
Well, it has occurred, and that's what Ferro's paper is all about. Ferro's paper shows that that will be at some mass, when the mass of the black hole gets to a point, there will be singularity. That is that point of no return, and it's what the prediction is all about. Thank you. That is quite an advanced question, and maybe not what we can discuss here, but it's what Penrose did, and got his Nobel Prize on. He showed that there is a point of singularity in the horizon that we are dealing with. Okay?
So we have another question. The person says,
this will have to be the last question, so that we can keep to our schedule to close in 5 minutes time, please.
Okay. So the question is, how do black holes collapse to create gravitational waves?
How do
black holes collapse to create gravitational waves?
black holes we collapse under the gravitational compaction coming from outside. It will keep on compacting until the threshold where it becomes a black hole from the density that it will reach. And let me illustrate that. Theoretically, we know that if the Earth, as we have it now, can be compressed to the size of a cube of sugar, it will become a black hole. That's the Earth as we have it now. If you can compact it to a high density that the size becomes that of a cube of sugar, it will transform to a black hole. That is a prediction from Penrose. Thank you very much.
Okay, so I guess.
Thank you. Oh, thank you, Dr. Oluwaseun Adegoke. And we're extremely very grateful to Professor Idufaraye for that presentation. Obviously, it is getting very, very interesting. Today, I think we had more participants than yesterday. Hopefully tomorrow, which is going to be economics, we'll have more. We really thank you and I appreciate your coming on board, sirs. On behalf of the board and the executive of RACD, I thank every participant for sparing time to join us. We hope to see you tomorrow. Good night and God bless. Thank you.
Thank you.